and welcome to this video. This is EDEXCEL topic 4, Inorganic Chemistry and the Periodic Table. My name is Chris Harris and I'm from AlleryTutors.com, and basically in this video we're going to give you a quick overview to the Inorganic Chemistry and Periodic Table topic. This is specifically for EDEXCEL. Now the slides that I'm using here, you can purchase them, you can use them for revision. They're really good value. And you can use them for revision on your smartphone, your tablet. You can print them off, and good way of supplementing your revision notes. Just click on the link in the description box below this video, and you'll be able to get a hold of them there. Right, like I say, these are specifically for EDEXCEL, so they match this specification from the syllabus. So if you're studying EDEXCEL, then this should be perfect for you. Okay, so let's start by looking at atomic radius, because obviously this is about the periodic table. So the atomic radius. Basically, group 2 elements, they form +2 ions when they react. Okay, so all group 2 metals, they lose 2 electrons to form +2 ions. Okay, so all group 2 metals have electron configurations and they all end in S2, as you can see here. So all the ones that are going to be circled here, that shows that they all end in S2. Now notice the ions on the right hand side, that the S2 has been lost from the ions for Be2+, Mg2+, and Ca2+. Okay, so the atomic radius increases as we go down the group, so it gets bigger. And you can see from this graph, there's the evidence. We start from beryllium over here, we go up to barium, and you can see the atomic radius is increasing. Remember, radius measured in nanometers is really small. Okay, the reason why is because we're adding extra shells as we go down group 2. Okay, so this can be linked with ionization energy, and the first ionization energy decreases as we go down group 2. So all this stuff is to do with group 2 in particular. Okay, the reason why is because we've got these extra shells. Remember that from the last slide. As we go down the group, we've got these extra shells. Now, if we've got extra shells, we have more shielding. Therefore, we have a weaker attraction between the nucleus and the outer electrons. So what this means is that the outer electrons are further from the nucleus, and this weakens the attraction. Now you can see both of these effects here make it really easy to remove the outer electron. Less energy is needed, so therefore the first ionization energy drops. And you can see here from beryllium, which is top of the group, down to barium, which is down at the bottom. So you can see the first ionization energy decreases. So it's becoming easier to remove that electron. Okay, now you do have an increased number of protons as we go down the group. We do have more protons. However, the shielding effect overrides any increase of positive charge, so make sure you mention that in the exam if they ask about it. Okay, so let's have a look at the reactions with water. So all group 2 elements, they react with water to form bases. They're actually called alkaline earth metals, and the reason why is because they form alkaline solutions or bases. So they react with water to form metal hydroxides, and here's an example here. This is strontium reacting with water, forms strontium hydroxide. Notice the brackets with the 2 means we need 2 lots of OH per strontium atom. And hydrogen gas is produced. This is very similar to the group 1 metals when you add them to water. They're a lot more violent though than group 2s. And you add them and they catch fire and produce hydrogen gas. Now the reactivity increases with water as we go down the group. So beryllium actually doesn't react at all down to barium, which would react reasonably strongly with water. And the reason why is because the atom gets bigger. So again, it's this size of the atom. The electron's further away from the nucleus. It's much easier to remove that electron because it's further away from the nucleus. That means it's more reactive. And also, get that word in there, shielding. Okay, you're seeing this quite a lot. There's more shielding between the nucleus, positive nucleus, and the outer electrons. Magnesium, it reacts slowly with cold water. It does react, so it's more than beryllium, but it reacts much more vigorously with steam, and actually it produces magnesium oxide instead. So instead of a hydroxide, we're making an oxide. So just be wary of that, and just make sure you have that just in the back of your mind if they ask about magnesium. Look out for your state symbols. If it says H2O gas, that means it's steam. Okay, so just make sure you look out for your state symbols. They might do it subtly like that. Okay, so group 2 elements, they also react with oxygen, and they also form bases, because oxides or metal oxides are bases. So we're going to react this with oxygen, and here's an example. This is magnesium. You might have seen this before. Magnesium ribbon, put it in a Bunsen flame with a brilliant white flame, and you form this white powder of magnesium oxide. Now, if we look at the oxidation number of magnesium, starts off as 0 because it's an element, and it goes to +2 because it's combined with oxygen. So you can see the magnesium is being oxidized because there's an increase in oxidation number. Now your oxygen is being reduced. It's going from obviously an element, which is 0, and the oxygen, because it's combined, is -2. So we've got oxygen being reduced and magnesium being oxidized. So this is a redox reaction. Okay. Group 2 oxides, they're all white solids. So magnesium oxide, you're probably more familiar with. You'll get this white powder that's produced after you've burnt your magnesium ribbon. Okay, so group 2 elements, they react with chlorine because they form chlorides. So reaction with chlorine to form metal chlorides, like I say, here it is here. Again, we're going to use magnesium. Dead easy, this one really. Magnesium solid, react with chlorine gas, forms magnesium chloride. You couldn't really get much simpler than that. It is a solid. Again, look at your oxidation states. Magnesium has been oxidized. We've got an increase in oxidation number. And your chlorine has been reduced. It's gone from Cl2 as an element, remember it's 0, to combined chlorine. Now each individual chlorine is -1, so that's been reduced. Okay, they form bases when they're reacting with water as well. So these are your group 2 oxides, should we say. So you take your oxide and you add it to water, and alkaline solutions are formed. So let's have a look at some examples. Here's strontium oxide reacting with water, and it forms strontium hydroxide. Okay, so this is what makes it a base. And if we look at this one here, this is basically just showing the ions that are formed. Strontium oxide plus water forms strontium ion, Sr2+. It's aqueous because all ions are aqueous in solution. And OH-, this is what makes it a base. It's the amount of these. The more of these you've got in the solution, the more basic it is. Okay, and this makes it aqueous. Okay, so oxides, they react readily with water to make hydroxides, and they dissociate to form the OH- that we've just shown you there. Okay, magnesium oxide though reacts really slowly. Okay, and the hydroxide barely dissolves, so therefore it's not as basic as some of the ones lower down in the group. And beryllium oxide doesn't react with water at all. Okay, and the hydroxide is insoluble, so in that case, beryllium oxide doesn't form a basic solution because it doesn't dissolve. And they become more strongly alkaline, like I say, as we go down the group. The hydroxides become more soluble, they dissociate, and that means that you get loads of these OH- ions in your solution. Okay, so that's really important. It's all about dissociation of your hydroxide. The more readily it dissolves, the more it dissociates, the more of these OH- you got, and the more alkaline it is. Okay, neutralization. Now, because these are alkalis, we can neutralize acids. So, like say, group 2 oxides and hydroxides, they are bases, so we can use them. Like I say, they can neutralize acids. So, for example, this is how an oxide reacts with an acid. So you just take calcium oxide, which is your base, plus acids. It's acid plus base forms salt plus water. Okay, it's the same type of reaction. There's nothing different here. You're just taking the metal and the non-metal from the acid and combining them together to form your salt, and you always produce water. So really, if you just remember that, acid plus base gives salt plus water, you should be fine. And it's exactly the same with hydroxides as well. Look, there's your base, there's your acid. Acid plus base gives salt plus water, okay? It's the same type of reaction. All you have to do is just balance it, okay? So make sure you can effectively write these down and balance them, because you get a decent, reasonable amount of marks for what is effectively just a relatively straightforward equation. You'll see a lot worse than these, really. Okay, so sticking on group 2, we're going to look at solubility, okay? Because we looked at, obviously, these compounds being able to dissolve. Now, group 2 hydroxides and sulfates, you need to know in particular, okay? And they actually have opposite solubility as we go down the group. So let's have a look. As a general rule, if the anion, which is the negative ion, if it has a double charge, they become less soluble as we go down the group. So you can see here that magnesium is really soluble. It dissolves really well, magnesium sulfate. But barium sulfate doesn't. It's sparingly soluble. It doesn't dissolve very well whatsoever. Generally, though, if the anion, like the negative ion, is a single charge, then they become more soluble as we go down the group. So, for example, barium hydroxide is really soluble, but as we've seen in the previous slide, magnesium hydroxide doesn't really dissolve very well whatsoever. So we say it's sparingly soluble. Okay, so we'll look at some decomposition. Now this can get a little bit tricky, so you need to really listen to this carefully. Okay, so group 2 carbonates and nitrates, okay, they can decompose upon heating. So we're just heating these strongly under a Bunsen flame. Now carbonates break down into metal oxides and carbon dioxide. Again, carbonate, carbon dioxide, okay? This occurs via thermal decomposition, just means breaking a compound down using heat. So here's an example of the equation. Calcium carbonate, notice we've got no other reactant there because it's decomposition. It's a classic sign of thermal decomposition when you just have one solid at one side in products. So calcium carbonate forms calcium oxide plus carbon dioxide. Got to remember that. Now, nitrates, they break down into metal oxides, nitrogen dioxide, and oxygen, again via thermal decomposition. So let's have a look. These produce a little bit more. There's calcium nitrate there, okay? This is going to produce your oxide, just like as before, but this time, instead of carbon dioxide, you're going to produce nitrogen dioxide and oxygen gas. Okay, so you're going to produce 3 products. Make sure you're aware, especially these 2 at the end. So carbonates and nitrates, they become more thermally stable as we go down group 2. Okay, so the carbonate and the nitrate ion, or either of them, they have a large electron cloud because they're quite big molecular ions, and these can be distorted when nearby positive group 2 metal atoms. Okay, this is where it gets a bit tricky, you see. So all group 2 metal ions, they have a 2+ charge. However, they become larger as we go down the group, meaning the charge is spread over a larger area and they have a larger, lower charge density. So this charge density, this idea of charge density, you're looking at the size of the ion and you're looking at the size of the charge. The bigger the ion, the more that charge is spread over a larger area. And that's going to have an impact on how it distorts the electron clouds in your carbonates and nitrates. Okay, so let's have a look at an example here. So we've got magnesium 2+ has a really high charge density. 2+ charge, obviously all of them are 2+ charges, but your magnesium is smaller, is a smaller ion. So it has a higher charge density. It distorts the electron cloud in the carbonate and the nitrate ions more than in barium 2+, which is a much bigger ion, and this is a lower charge density. So actually the distortion you see is much greater in the carbonate than it is with the barium in the carbonate. And basically the less distortion we have, so like this, the more stable the carbonate is. So this is the most stable carbonate, which is barium carbonate, compared to magnesium carbonate, which is less stable. Okay, got to remember that little bit. It's a bit tricky. You just got to bear with it. Okay, right. So group 1 carbonates. Okay, so we looked at group 2. We're looking at group 1 now. These can also decompose upon heating and are more thermally stable than group 2 compounds. Okay, so we're now making this comparison between group 1 and group 2. So make sure you're aware of that. So carbonates, they are thermally stable under a Bunsen, okay, except for lithium carbonate, which forms an oxide and carbon dioxide. Okay, so let's have a look. Here's the lithium carbonate example. So lithium carbonate forms your lithium oxide and carbon dioxide, but generally the group 1 carbonates are thermally stable. Okay, so lithium carbonate is just the exception there. Nitrates, they break down into nitrites and oxygen, except for LiNO3, which decomposes to form lithium oxide, nitrogen dioxide, and oxygen. Okay, so little exceptions here. Here it is here, look. Potassium, here's yours, KNO3, this is potassium nitrate. Okay, it forms potassium nitrite, NO2, this is called nitrite, and oxygen. Make sure you know the difference between them. Look how similar they are. Okay, NO2 is nitrite, NO3 is nitrate. Okay, so this is obviously showing the decomposition. And again, if we look at the group 1s, okay, if we look at both of them, if we compare the two, so there's a group 1 which is sodium, and there's a group 2 which is magnesium. So magnesium 2+ has a high charge density, distorts the electron cloud in the carbonate and nitrate ions more than the sodium does because it's got a much bigger charge density. This means that there's less distortion the more stable the carbonate is. So again, sodium carbonate is much more stable than magnesium carbonate. Again, it's all about this distortion of the negative molecular ion, which is the carbonate. So the less distortion you've got, the more stable it is. Just remember that. Okay, it's all about this charge density here. It's pretty tricky stuff, that. Okay, so we're now still on this stability bit. We're going to be testing them, okay? And we can test the stability of nitrates and carbonates experimentally. So we can say, right, well, how do we know how stable something is? So if we look at nitrates first, okay, so what we can do is measure how long it takes to for a specific amount of oxygen to be produced. So remember, one of the products of the decomposition of nitrates as the oxygen that's produced. And what we can use is just use a gas syringe, and obviously we can put it into a flask and a bung, put a delivery tube onto a gas syringe, and then measure, see how much comes out. Or you can measure basically the amount needed to relight a glowing splint if you want. So you can do it a few ways. Another way of doing it is basically taking the length of time it takes to produce a specific amount of NO2. Because remember, that was one of the other products that we produced. Now, the good thing with NO2 is that it's a brown gas, so we can see it dead easily. It's toxic though. You don't want to breathe this stuff in, so you've got to put it into a fume cupboard. Okay, so nitrogen dioxide can form nitric acid, and it's really corrosive, so you really don't want to breathe this stuff in. Carbonates, on the other hand, so the length of time it takes until a specific amount of carbon dioxide is produced. Again, we're all looking at these gases, we're measuring them in terms of gases. Carbon dioxide obviously turns your lime water cloudy, so the quicker it turns it cloudy, the more carbon dioxide is produced. Or you could use a gas syringe. Probably the gas syringe is probably the better one, because you can quantify it much easier using a gas syringe than you can with, obviously, the speed at which lime water turns cloudy, because you've got quite a bit of error in that one. So yeah, the gas syringe is probably the better one for that one. So you're just measuring how much gas you're producing over time. So it's pretty straightforward, really. Okay, so flame tests. So we can test for positive ions, okay, it's called cations, in a compound, and we can use flame tests. Okay, so we got all these different colours that's appearing. You might have heard, you will have done, which is your line spectrum. Remember about electrons jumping between shells, and obviously absorbing that energy. We'll call it quanta. So why we get different colours? So the electrons in the shells, they move to higher energy levels as they absorb energy from the flame. Okay, when they drop back down to lower energy levels, the light is released. And different colours are produced as the difference in energy levels determines the wavelength of light released. Okay, so we're looking at basically the electrons jumping back down, giving off this bit of colour. And obviously we're looking for that as well. But if you look at topic 1, you'll see a lot more about that as well. So I'm not going into it too much here. Now, when we test, we need to use what we call nichrome wire. Okay, it's just a bit of wire, and you might have a cork on the end of it. You dip it into some concentrated hydrochloric acid just to try and clean it. Dip it into the sample. It'll help the acid will also help the sample to stick to the wire. And then we place the loop into the blue Bunsen flame. It must be blue. Okay, and we observe the colour. Now, you need to know some of these colours here. So, lithium is crimson, sodium is a yellowy orange. You might have seen sodium street lamps, these orange street lamps. Potassium is lilac, rubidium is the red colour, rubidium red. Cesium is blue, calcium is dark red, strontium is crimson, and your green is your green flame is caused by barium. Okay. Right, so let's have a look at some halogens. So the halogens make up group 7 of the periodic table. So we've looked at a bit of group 1, we've looked at some quite a bit of group 2, so now we're looking at group 7. Okay, so the halogens make up group 7 of the periodic table. Fluorine is a pale yellow gas, and look at the electron configuration: 1s2, 2s2, 2p5. Chlorine is a pale green gas, and we get a little bit darker now, but we've added, you can see, we've got the extra electrons now in here. We've got the 3s2, and obviously we've got the 3p5 electrons now. Bromine, again, a bit darker again, browny orangey liquid, and there's the electron configuration. And iodine is a grey solid. Now, you notice obviously going gas, gas, liquid, solid. We need to be able to know why. We're going to look at that soon. Okay, now, as we go down the group, the boiling points increase. Okay, so it takes more energy to boil these substances. Okay, so these molecules. So this is because we've got London forces increasing due to the increase in size and the relative mass of the atoms. So iodine is much, much bigger than fluorine. And the physical state, as you can see, goes from gas at the top of group 7 to solid at the bottom. Okay, so there's the literally physical evidence for these increased melting points, because at room temperature they have different states. Electronegativity decreases as we go down the group. Remember, electronegativity is the ability for an atom to attract electrons towards itself in a covalent bond. And as we go down the group, the atoms get much bigger, and the distance between the positive nucleus and the bonding electrons, that increases. And so obviously we've got more shielding as well between the positive nucleus and the outer electrons. So this means that the ability to pull electrons towards itself is much reduced in iodine compared to fluorine. So fluorine is a lot more electronegative. Okay, displacement reactions. So what we can do is we can add hexane, and it makes it easier to observe some of these colours. So when undertaking halogen displacement reactions, we can add an organic solvent, like I say, like hexane. You can see the colour really easily. Now you can see this kind of as a diagram. So basically the halogen present, okay, the halogen ion that's present will dissolve readily in that organic solvent, okay, and that forms a layer above the aqueous layer. And we get a coloured band, and depending on the colour of the coloured band will tell you what ion we've got and the displacement that we have as well. Okay, so let's have a look at some of these colour changes. So remember, a more reactive halogen will displace a less reactive halide ion. Okay, so we're talking about remember the reactivity, fluorine is the most reactive element, and as we go down the group, they become less reactive. Okay, so remember this, decreases as we go down group 7. Okay, and the reason why, for a reaction to occur, an electron is gained. Okay, so we're gaining electrons, and the atoms with a smaller radius, they attract electrons better than ones with larger atoms. Okay, so they pull electrons towards themselves much more readily, and that means they're more reactive. So halogens are less oxidizing as we go down the group. And we could show this by reacting the halogens with halide ions. We call this a displacement reaction. But remember, a halogen will displace a halide from its solution if the halide is lower in the periodic table. So we're going to talk through some of these. Right, so let's have a look at the first one. Obviously, we've got no reaction here. We've got, obviously, addition of chlorine water. Chlorine atom and chloride ion are both just as reactive, so we get no reaction. But if we come into this one, though, you can see here, chlorine is more reactive than bromide ions. It's higher in the periodic table, so we get a yellow aqueous layer and an orange organic layer. Here's the ionic equation, look. Chlorine reacts with the bromide ions, we get a displacement. We get chloride ions and bromine, which is Br2. And we're looking for this orange band within the organic layer, which is at the top. Again, we get a reaction here as well. So for chlorine is more reactive than iodide. So in the aqueous we get brown, in the organic we get a purple colour. And again, here's our ionic equation showing it. Obviously we get no reaction here with the addition of bromine water and potassium chloride solution. We get no reaction because obviously the bromine is less reactive than chloride. It's lower in the group. Obviously, we've got no reaction here as well because it's bromide and bromine. They're just bromide there and bromine. They're both just as reactive. And obviously, we do get a reaction here with this one. So bromine is more reactive than iodide. So we do get a reaction. Again, we get this purple in the organic layer and brown in the aqueous layer. And there's our ionic equation. Now, you can see here that for the addition of iodine solution, we get no reaction here. Iodine chloride is more reactive than iodine, so we don't get a reaction. Bromide is more reactive than iodine, so we get no reaction again. And finally, iodine and iodide are just as reactive with each other, so again, we get no reaction. Okay, so we get no change in these colours here. Okay, so reactions with group 1 and 2 elements. Okay, so halogens, they react with group 1 and 2 elements and they form metal halides. So let's look at this example. Magnesium metal reacting with chlorine forms magnesium chloride. So again, it's pretty straightforward. Okay, look at the oxidation states. We're going from 0 in magnesium to +2. So the magnesium is being oxidized here. And your chlorine is being reduced. And you see we're going from 0 to -1. Now notice the equations here, the half equations. Magnesium going to Mg2+. We balance it with the 2 electrons. This shows it's been oxidized. Okay, remember oxidation is the loss of electrons, so magnesium is being oxidized. Whereas this one is showing that chlorine is reacting with the 2 electrons to form chloride ions. So this is reduction, because reduction is the gain of electrons. So chlorine plus 2 electrons forms chloride. So this is just showing a half equation. Okay, lithium and chlorine forms lithium chloride, which is LiCl. Okay, so this is obviously group 1. Again, look at the oxidation state. Lithium is being oxidized. Okay, it's gone from 0 to +1. There's the half equation for it. And your chloride has been reduced. It's going from chlorine, sorry, has been reduced. So chlorine's gone from 0 to -1. So there's the half equation there. Chlorine, Cl2, picking up 2 electrons to form 2Cl-. Okay, so that's the half equation for it. Okay, halogen ions. So the most halogen ions, they have different oxidation states. Okay, so if we have a look here, chlorides and bromides, these ions, we're just giving them -1. Okay, chlorine and bromine atom is 0 because they're just an element. Chlorate 1 is ClO-, that has a charge of +1. Remember, oxygen's -2. Overall, this has got a negative charge, so chlorine must be +1. This is called a chlorate 1. Bromate is pretty much the same as the explanation for chlorate. Bromate 1. Now, bromate 3, the little Roman numeral tells you the oxidation state of the bromine. This one, again, oxygen's -2. You've got 2 of them, so that's -4. Overall, it's got to have a negative charge, so bromine must be +3 in this case, so we'll call that bromate 3. Iodate 3, iodate, which is this one here, iodate 5, which is +5. Again, oxygen's -2, you've got 3 of them, that's -6. Overall charge is minus, so the iodine must be +5 to make sure you get the overall charge. That's called iodate 5. Notice they all in H because they're bonded with oxygen. You can also get iodate 7 as well, which is, again, same reason. 4 times -2, because oxygen's -2, is -8. The whole thing must be minus overall, so the iodine must be +7. So you can see here, these halogens have loads of different oxidation states, but look at the Roman numerals. That tells you the oxidation number of the halogen that it's attached to. They all end in 8 because they're all bonded with oxygen, so you can work them out from there. Fluorine only forms oxidation states of 0 and -1, so it's not as versatile as the rest of them, and they can't form positive oxidation states like some of these halogens here, like chlorine, bromine, and iodine. Okay, disproportionation reactions. Okay, so halogens react with cold alkalis. Now, there's a difference here because we're going to look at cold and then we're going to look at hot alkalis. So these are the ones with cold, and these go via a disproportionation reaction. So let's have a look at the general equation. X2 represents a halogen. React that with sodium hydroxide and we form this. X is the halogen. Okay, so we form our chlorate like we've just seen before. Sodium chlorate 1 this would be if the X was a chlorine, of course. Sodium chloride here and H2O. Again, the X represents the halogen. So here's the ionic equation for it. X2, the sodium spectator, because it doesn't play any role, hasn't changed here. It's +1 there, it's +1 there, it's +1 there. So because it hasn't changed in the products and reactants, we can ignore it. So we just write down the hydroxide bit here, OH-. OX- is obviously that bit without the sodium. The X- is again without the sodium, and water. So we just remove the sodium because that's a spectator ion. That's the ionic equation. Now you can see here, again, we're looking at the oxidation number of X. This is the halogen. You can see here that's 0 here because it's elemental. But the halogen here is +1 and the halogen here is -1. Okay, so you can see here the same halogen is being oxidized and reduced. And we call this a disproportionation reaction when we're getting simultaneous reduction and oxidation. Now, here's a proper example. Here's the bromine this time. We react that with sodium hydroxide, and we're going to form sodium bromate, a bit like the examples we've seen before, sodium bromide, and H2O. Okay, so it's been simultaneously oxidized here and reduced. So that's an example of this one. Now, it's this bit that you want to watch out for when we're dealing with hot alkalis. So I want you to pay particular attention to that. Okay, so these are the ones with hot alkalis. Again, look at this equation. Number of halogens, sodium hydroxide, so it's 3X2, 6 NaOH, and look at this, look at the difference here. This forms sodium XO3, okay? X represents halogen. Then you form your sodium halide and water. So it's this bit that really changes, and obviously it knocks all these off balance as well. So here's the ionic equation. Again, we've chopped the sodiums off because they're just spectators, just like before. And this is the ionic equation for the general ionic equation. So you can see here that we've gone from an oxidation state of 0, which is X2, and this time the halogen here is +5. Okay, remember, look at the examples we showed in 2 slides ago. This is a +5. Okay, so this is a halate +5, a halate 5 ion. And this is a 5X -1, is obviously, this is just -1. You can see here that we've got oxidation and reduction simultaneously. So we call this a disproportionation. Let's look at an example. This is chlorine this time. So this is going to be 3Cl2, 6 NaOH. Look at this one, sodium chlorate 5. Okay, we form chlorate 5 with hot alkalis. Okay, not chlorate 1 if it was with a cold alkali. Again, we still produce our salt, sodium chloride, and water. But this is just an example showing what's happening. Okay, bleach. So bleach is also a disproportionation reaction. Now, obviously, you've heard of bleach before. Bleach is obviously this fantastic chemical because it kills bacteria, it kills it in our drinking water, and obviously it kills it in swimming pools and toilets and things like that. So it's pretty useful. Okay, mixing chlorine and sodium hydroxide will form sodium chlorate 1 solution. Okay, and this is also known as bleach. So here it is here, sodium hydroxide reacting with chlorine gas forms your bleach. There it is there, sodium chlorate 1, sodium chloride, and water is also produced. Now, if you look here, the chlorine's got an oxidation state of 0 because this is an element. Your chlorine in sodium chlorate 1 has an oxidation state of +1, and chlorine in sodium chloride is -1. So you can see this is a disproportionation reaction. Chlorine's been oxidized and reduced. So, again, it's just the same as the other reactions. You'll see disproportionation, obviously, it's come up in a few different guises. So, like I say, we can use sodium chlorate, which is bleach, for treating water, which is obviously tap water. Bleaching paper and fabrics, make it really white. And cleaning agents, obviously, like I say, you can clean toilets with it. Okay, let's have a look at this water sterilization, because this is quite important. So, adding chlorine to water can kill bacteria in water. Now, this is slightly different to bleach. It's similar in a way. You're still producing the chloride ion, but it's just a different reaction. So, we're adding water to chlorine. Okay, so instead of sodium hydroxide, we're adding water. Water to chlorine. This will produce your chloride ions, again, just like what before. Now, this kills bacteria. Okay, so bacteria can't survive in this. Useful in drinking water and, like I say, swimming pools. So here it is again. Look at your oxidation states of each of these. Chlorine, yet again, has been simultaneously, that should be pointing to chlorine. That's oxidation state of 0, that's -1, and that's +1. You can see it's been simultaneously reduced and oxidized at the same time. So this is a disproportionation reaction. Now, chloric 1 acid, okay, this is HClO. This ionizes to make chlorate 1 ions. You can see here, there it is there. It's chloric 1 acid reacting with the water, so it deionizes or it splits. And you get ClO-. These are called hypochlorite ions. And you get these hydroxonium ions. This is what makes it acidic, H3O+ ions. Okay, so as long as you're aware of this chloric 1 acid and how it dissociates into these products, that's the main thing. Okay, so let's have a look at some reducing powers of halide ions. So halide ions, they lose an electron in reactions, so they are really good reducing agents. So remember, reduction is the gain of electrons, okay, but reducing agents lose electrons, okay, because reducing agents are themselves oxidized, so oxidation is the loss. Got to know the difference between a reducing agent and reduction. There is a difference. Okay, so as we go down the group, the ionic radius increases. Okay, so we already know that. We've got more shells there, more shielding. Okay, and the distance between the positive nucleus and the outer electrons becomes larger, and so therefore the attractive force gets weaker. Now what this means is this outer electron's lost a lot more readily, and this is the reason why I- is a more powerful reducing agent than F-. And there are two tests that we need to know. Okay, first one is the one with sulfuric acid, which is probably one of the most difficult things I think you'll probably see. Hopefully it won't be difficult when I go through it. And the reaction with silver nitrate solution. Okay, so we've got two tests in which we can prove this trend. Okay, so let's have a look at the ones with sulfuric acid. Now, I've got to mention this right now. You must know how to balance half equations, okay? You're going to struggle with this if you don't know how to do this. So if you're not sure, then take a break now. Make sure you get familiar with how you balance half equations using water, proton, and electrons, because that's what I'm going to be assuming that you know for this bit of the video. Okay, so some halide ions, they can reduce sulfuric acid. So what we've got is we've got our reduction products here. Okay, so we're going to add basically concentrated sulfuric acid to one, like a halide ion, for example. And the halide ion can reduce the sulfur in sulfuric acid, and it can reduce it to these products. Now, this isn't a reduced form from sulfuric acid, but these three are reduction products. Okay, and the oxidation states of sulfur, again, this is sodium hydrogen sulfate, this is +6. Sulfur dioxide is +4, sulfur is 0, and obviously this H2S is hydrogen sulfide, which is -2. Okay, and what we're going to do is going to use this kind of like little underground symbol, hopefully to kind of like a train map to kind of explain what's going on. Right, we're going to look at what happens with reaction A. Now, chlorides, bromides, and iodides, they all produce this product here, which is sodium hydrogen sulfate. So we just need to be aware of obviously how these are made. See, with sodium chloride, this is not a redox reaction. These ones here, this is just H2SO4 reacting with sodium chloride. That's like a salt, and that forms sodium hydrogen sulfate and HCl. Now this one, obviously, that should say sodium bromide, and that one says sodium iodide, so that's a mistake. A bit of a typo, almost got carried away with sodium chloride. But anyway, same reaction. H2SO4 will form, that should say sodium bromide, will form sodium hydrogen sulfate and HBr. And sodium iodide, again, sulfuric acid with sodium iodide, that should say, will form sodium hydrogen sulfate and hydrogen iodide. Now, basically, these are not redox because sulfur's +6 here and it's also +6 here. This is just merely a reaction in which you're reacting your salt with an acid. So you get white misty fumes though with chlorides, and chlorides, that's all it produces. Chlorides aren't very powerful reducing agents, so they don't reduce anything actually. And basically you just form this sodium hydrogen sulfate. However, these two, as you can see, they go on further to reduce the sulfur. So actually this product here reacts further. So let's have a look at these two. So we're going to look at bromide ions will produce sulfur dioxide and iodide ions will produce sulfur dioxide. So let's see the equations. Now this is where we do get half equations. And we need to know how to balance them. So this is at point B. So this is in addition to A. Okay, it's not instead of, it's been in addition to. So with sodium bromide, okay, let's have a look at the reactions here. Now, the bromide ions are being oxidized to bromine, which is Br2. So this is the first half of the equation. Okay, so bromide going to bromine. The other half is sulfuric acid being reduced. So you can see here, sulfuric acid, how you should do this is you write sulfuric acid first, and then you write SO2. And then what you do is you then balance oxygens with water, so we added 2 H2O here, then balance hydrogens with H plus ions, so we add that there, and then we balance the charges with electrons. Again, you must know how to do these, okay? So if you're not sure, take a break and look at this stuff first. Okay, and then what we do is we just combine these two electrons, cancel them out. We write our overall equation here. So this is sulfuric acid, react with the bromide ions to form bromine and sulfur dioxide. Okay, iodide ions will do exactly the same as well. Now for bromide, that's as far as it goes. It can reduce sulfur, and it's reduced it to +4. But iodides are really powerful, and they go further. Now this one is reaction C. Now only ions can produce this. So this is basically reducing. So iodide ions are going to I2. Okay, initially, and obviously balanced with electrons. Sulfuric acid is going to sulfur. Okay, and again, we're balanced with waters, H pluses, and electrons. Now, the main difference here is that actually we get 6 electrons here, but we only get 2 here initially. So to balance the electrons, we have to multiply the top equation by 3, so we get 6 electrons and we can cancel them out. Now, for those who are mathematically inclined, you might have seen, or even if you're not, you might have seen this as a simultaneous equation. So we're just cancelling out, we're getting, in this case it's chemistry though, so we're just cancelling out electrons, but it's always electrons to cancel out. So make sure you multiply the top one, so we get an equal number of electrons in each one, cancel them out, rewrite your overall one, there should be no electrons in your overall equation. Look out for the yellow solid produced, this is sulfur being created. Classic sign of iodide ions, because it's the only one that can produce sulfur. And it goes even further. Yes, it hasn't finished there. Iodide ions can reduce the sulfur even further down to H2S, which is hydrogen sulfide gas, -2. Look at the oxidation state here, really reduced. Iodide ions again going to I2. So we've got the same type of thing going on here. Sulfuric acid going to H2S, again balanced with water, protons and electrons. We need to multiply the top one by 4 this time to get 8 electrons. Again, cancel them out. Write your overall equation, and you can see that we get this H2S. Now, the classic sign that you're producing H2S, which is hydrogen sulfide, is this rotten egg smell. It's really horrible. It's really toxic, this stuff. Normally known as sewer gas. Normally when you kick sewage around in a sewer, you might have seen these sewerage people on the TV. And then it does kick up this horrible smell, and obviously sewers are stinking anyway, so these people they can't distinguish between just the normal sewage smell and this, so they have to wear badges and the badgers will basically warn them of high levels of H2S, and they've basically got to get out of there because they can't breathe this in. It's really toxic. Okay, so hydrogen halides, they're acidic. Okay, so if we look here, we've got hydrogen halides. They're all gases that dissolve in water to form acidic solutions. So remember, these were the products of the first step, step A. Okay, and they form white misty fumes as well when they're in air. Okay, so you can see here, HCl will dissociate to form H plus and Cl minus. That's what makes it acidic. Or if you dissolve it in water, again, you form this. This is just another way of writing it. Hydronium ion or hydroxonium ion. This is what makes it acidic. And obviously you produce your chloride ions. In reality, this is what you get. This is just a simplified form. Okay, so the hydrogen halides, they produce acids when they're dissolved in water. So hydrogen chloride produces hydrochloric acid. Hydrogen bromide forms hydrobromic. And hydrogen iodide forms hydroiodic acid. So very exotic names there for some acids, but you can see, I think you probably get the idea. Okay, so hydrogen halides, they also react with ammonia gas as well. They make these white misty fumes of this this salt that's being produced here. So we get ammonium halides. So this is a very straightforward addition reaction. Ammonia react with HCl and you form ammonium chloride, okay, which is this product here. Okay, so let's look at the other test, because obviously the sulfuric acid one is pretty nasty. Some really horrible products being produced there. This one's a little bit safer, thankfully, and a bit easier to remember. So, testing for halides using silver nitrate, and we confirm with ammonia solution, okay? So, basically, we're testing for chlorides, bromides, and iodides. And all it does, we just involve a little bit of dilute nitric acid first. I'll explain why we add that later on. And then some silver nitrate solution, which is AgNO3. And the colour of the precipitate basically tells you what the halide ion is that we've got. So chloride ions form a white precipitate. They react with your silver nitrate and they produce, there's the silver ion, look, from silver nitrate. There's the chloride ion from the halide, and that produces silver chloride solid. Notice it's a white precipitate we're forming, that's a chloride ion. Bromides form cream precipitates. Again, there's your half equation showing what's happening. Bear in mind, the solid product here is silver bromide. That is the actual, that's the colour of it, it's cream. And iodides form silver iodide, so that's yellow. This is a yellow precipitate that's been formed. Now, that nitric acid I was talking about, basically we add that before we add our silver nitrate because the nitric acid actually mops up any carbonates that are present in the water. Remember, this silver nitrate solution, the silver can react with the carbonate and form a precipitate. That would give you the impression that actually, oh, you've got a chloride ion, and actually you don't, because the silver has actually reacted with carbonate ions and is given a false positive. So basically, we just add the nitric acid to remove these carbonates so they don't get in the way. And now, you might think, actually, well, they look pretty similar colour, and you're right, it's really difficult to distinguish them. So thankfully, we've got a further test that we can do to really just rubber stamp that we know what ions we've got here. So we're going to add ammonia to this. Now, if we add dilute ammonia to all three initially, what you'll find is that your chloride ions, the white precipitate, will dissolve. So silver chloride is soluble in dilute ammonia, but it doesn't dissolve any of these. So that basically tells you, right, that must be chloride. To these two then, if we add concentrated ammonia to both of these, then what we should find is the bromide one will dissolve. Okay, it is soluble. Silver bromide is soluble, so it dissolves when we add concentrated ammonia. But silver iodide doesn't. It's insoluble even in concentrated. So we know that when we add concentrated, the one that dissolves must contain bromide ions. Okay, now you might wonder where the fluoride is. Well, actually, fluoride ions, F-, they don't even form a precipitate. Silver fluoride is really soluble, so we don't even need to add any ammonia. It just dissolves anyway. So it looks as though no reaction's happened. It has. There is a reaction. It's just the product is soluble, so we don't see it. Okay, let's have a look at some of these tests for ions. So, testing for carbonates and sulfates. Obviously, we looked at the test for halide ions. Let's look at the other bits. So, we're going to use hydrochloric acid and barium chloride for these. So, testing for carbonates is pretty straightforward, to be honest. All we're doing is we add an acid to a carbonate. Hydrochloric acid will do. And basically what you form is hydrogen carbonates, or carbonates and hydrogen carbonates. Either of these can be tested. And we form carbon dioxide. Okay, this is the gas that comes through here. Now we can test to see if it is actually carbon dioxide by pushing it through some lime water, and if it turns cloudy, that's a classic sign of carbon dioxide being produced. Okay, testing for sulfates. All we do is we basically adding barium sulfate, but there's a little step that we have to do first, and that is to add hydrochloric acid. Again, this is to remove any carbonates. We don't want any false positives. If you get barium carbonate, you might get some precipitate being forming, and that might give you the impression you've got a sulfate. So we just add the HCl, removes any carbonates, and then we add barium chloride. If we have sulfates present, we should get a white precipitate being formed. And this white precipitate is barium sulfate. Now you can remember from a few slides back, we said that barium sulfate was insoluble, and that's why it shows up as a positive test. This is a great way of using effectively a group 2 metal to test for a group 2 compound, should we say, and testing for sulfate. And if obviously we get this white precipitate, and there's the ionic equation there. Okay, testing for ammonium compounds and hydroxide, we use litmus papers. It's pretty straightforward, this one. So testing for ammonium compounds, what we do is we add a bit of sodium hydroxide to the unknown compound that we think might contain ammonium ions, and basically we gently heat it. And if this ammonium compound is present, we should get ammonia gas being produced, and that really stinks because you can smell it. And basically we take a bit of litmus paper, dampen it, some red litmus, and it will turn it blue, to signify that we've got an alkaline gas being produced. So again, you can see the ionic equation. This is ammonium ions that might be present in here reacting with the hydroxide ions, and what these do is it liberates the ammonium ions, turns obviously the OH minus accepts the proton to form water, and we get ammonia, which then drifts off, and we can test it with a damp litmus. Okay, and then testing for hydroxides. Again, these are alkaline, and they will turn red litmus blue, so that's one way in which we can test for hydroxide. The problem is, though, doesn't tell you that you definitely have a hydroxide, because a lot of things turn red litmus blue. So what we need to do is we need to do further tests. So you can use spectroscopy to help to identify, for example, an alkali, which is an OH minus. Okay, and that's it. Quite a big topic, as you can see, but that's basically an overview of topic 4 for inorganic chemistry and the periodic table. Please support this channel by subscribing to it. If you just click on the circle in the middle, and you get all the updates, all the updated videos. As soon as they get put on, you can see them on there. Also, just a reminder, you can purchase these slides. You can use them for revision. Really great value for money. Just click on the link in the description box and you'll be able to get a hold of them there. But that's it. Bye bye.